Welcome back, Eigen family. So, guys, make sure you like, share, comment, subscribe as normal. And then also check out the website, eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok. And then patrons, guys, thank you so much for donating, supporting the channel.
Seriously.
Of course, we can't do without you, as we always say. And if you guys want to become a patron, just check out patreon.com/eigenbros. And you can sign up there for, audio podcast there at least every week, 30 minutes, guaranteed. And, let's jump in.
Let's jump in.
Unless you got anything else to add there, Juan.
No, fusion.
Fusion.
Now, we're not talking about like some kind of Asian kitchen fusion.
Although that would be probably a fun episode to do.
It might be more interesting than what you're about to see.
Honestly, yeah. I'm kind of about sick of Pais. But as you probably know, I told you, Juan, that I wanted to do this episode because we were getting some more hits on our Salvatore Pais episodes. Every now and then we get a smattering of people that keep coming back to visit those videos because, aliens sell. What are you going to do? So this one's for our alien audience.
If it's good enough for Joe Rogan, it's good enough for us. That's how most people don't acknowledge it, but that's how he got his
that's how we got our clout?
That's how he got his clout.
His clout.
UFO stuff, conspiracies.
I think he hit his peak with the UFO stuff.
Maybe it's
because he already had clout. Let's be real.
Yeah, as a musclehead comedy guy.
Yeah.
But anyway, you can maybe you should give the people a quick synopsis of who this guy is, Pais.
Yeah. So basically, Salvatore Pais is one of these. He's got a background in physics. He basically works for the U.S. Navy. He worked for a couple facilities. One is called NALCAD. The other one SSR, I believe. Check that. Not sure if that's true. But yeah, he's a U.S. naval researcher. He's got a background in aerospace engineering, physics. Worked with NASA. Has a PhD, doctorate. He's basically responsible for these weird UFO patents, as people have dubbed them. So he's made patents regarding an inertial mass reduction device. I think a piezoelectric superconductor, a high something gravitational field generator, and then of course the one we're talking about today is the plasma compression fusion device. So me and Juan have talked about a couple of those patents already. If you guys want to go back, we have episodes on the inertial mass reduction device, and then we have another episode on the piezoelectric superconductor. Or room temperature superconductor. So basically with this one, we're kind of doing a part 3, I guess you could say, in the series, talking about his plasma compression device. Mm-hmm. So I guess that's pretty much it. Did you have anything you wanted to add to that intro, Juan?
Yeah, Pais is a real person. He's not like one of these he's not a nameless, faceless
CIA construct.
Yeah, he's not some alias or something. Terrence literally spoke to his advisor.
Yeah, I did. I spoke to his advisor. I emailed him a while back, like a year or so ago, and talked to him about Pais, asked him what type of student he was. Was he a crazy motherfucker, basically? In more or less words.
Yeah.
And his advisor was pretty chill.
We have the documents, as Alex Jones would say.
Right. Well, his advisor was pretty chill about him and said, "Oh, he must be doing great things if you're inquiring about him." I'm like, he's doing things at least.
Yeah. Questionable, maybe.
But no, we're going to try to keep unbiased. I'm trying to put on my unbiased hat here and just try to give the facts, the straight facts. But I will just at least clarify, to let you know my internal bias that I do not believe that Pais has created these crazy technologies, but for the people who just really want to know and understand what's going on and have kind of a rough understanding from people who do have a physics background, this podcast will be for you, hopefully. For physicists, maybe not so much. You're probably rolling your eyes, so I don't know, you could skip this one, but the people who are interested, by all means stick with us and hopefully we can shed some light for you guys. So I guess
maybe later we'll talk about Asian fusion.
Maybe later. Yeah. So stick around if you really want. That's the what is it? The incentive to stick around.
That's the carrot for dangling. So
let's
get to it. What do you got? A couple videos pulled up?
Yeah. So I wanted to just basically talk about fusion first. So just to get people up to speed. So what the hell is fusion even? Why this is even relevant? What's the purpose of even Pais wanting to create a compact fusion device. So I guess let's start with the video on just nuclear fission of deuterium and tritium. It's a little bit different from Pius' patent because he likes to do deuterium reactions, but this is just a nice little basic intro to what nuclear fusion even is. So,
hello and welcome to Don's Lab. This is where I discuss science topics and hopefully you guys understand them a little bit better. So deuterium and tritium fusion. Deuterium and tritium are two isotopes of hydrogen. Tritium is made up of 3 subatomic particles, 2 neutrons, 1 proton. And deuterium is made up of 2 subatomic particles, 1 neutron and 1 proton. Alright? So when these two are collided together, they form a helium atom, which is 2 protons, 2 neutrons. Alright? So you may be asking, what happens to the other neutron? Well, during this release of energy, it shoots out 1 neutron because it cannot be used in this lightweight nuclei. Okay? So, the mass afterwards equals 4.98. The energy released from it is E equals 0.2.
By the way, this must be an engineer because he's not giving any units.
yeah.
Like, what kind of mass are we talking about?
Right. He will add a unit to the energy here in a minute, but yeah, the mass being 4.98 with no units is a very big tell. No physicist would ever do that, but those units are supposed to be AMU.
Gotcha. Okay.
Right. So, this particular fusion releases 676 units. Okay? And a unit is the amount of energy 1 U.S. citizen uses in a year. So, let's talk a little bit about deuterium.
Also, pause on that. I don't know if that's a real number either, so take that with a massive grain of salt. 676 units in one reaction. I don't know about that. I mean, he's making the claim that one tritium reaction is going to release that much for a person in a year, or what one citizen in the U.S. uses in a year.
Yeah.
I don't think that's true. So just take that with a grain of salt.
Yeah, maybe we'll throw a little picture up here. See, fact check this guy, right?
Yeah, well, I know the number the amount of energy that a citizen uses in a year, an average household, let's say, in joules is about 39 gigajoules.
Gigajoules.
But I don't know his unit is 676, whatever. But anyway.
Let's go.
And tritium. Deuterium is abundant, so you can find it pretty much in a lot of places. But tritium is more rare, okay? You can only find it by breeding lithium or get it from the deuterium cycle, which, if you guys ask me to do it, I might talk about the deuterium cycle. But so that's what deuterium and
So that's pretty good. So that's a nice little intro, right?
Yeah.
One of the other things I guess I wanted to add on to that, expound upon that, is that the deuterium atoms have this interesting property where you actually release more energy in a fusion reaction when the atoms combined, as opposed to a fission reaction, which maybe some of you are already familiar with in nuclear reactions, is when you have splitting of atoms. So deuterium actually has more energy release combining those two atoms than the inverse of that, which would be fission, which is pretty interesting.
Oh, I see. That is interesting.
Yeah. And that's just because the nuclear binding energy, for some reason, actually it releases more energy than fission. That's kind of like, doesn't really say that much, but that's just what it is, I guess. This next video will be kind of a nice little, driving the point home on these kind of reactions, and kind of will give you a little bit more detail on the nuclear fusion reaction. So we can watch that next one. Unless you have some questions
good, because I literally don't know anything about this stuff.
Okay, good.
So
yeah.
this is I'm actually learning with the audience.
Right.
So this is good. All right, let's go. Let's do it.
Consider the following nuclear reaction that uses deuterium and tritium as fuel. We have hydrogen 2, hydrogen 3, and they go to helium 4. Okay. Complete the reaction. What is the name of the new particle released during the reaction? All right, so the way we're going to do this is we're going to do a conservation of nucleons, the protons and neutrons. So here is the sum. This is the atomic mass of the isotope. So, and this is the number of protons. So we know here that we have 1, 2, 3, 4, 5 neutrons plus protons. And then we have a total of 2 protons. So I'm going to rewrite this here.
So for the audio listeners, he's just basically showing a stoichiometry equation of 2 deuterium atoms and then them yielding a helium-4 atom.
As helium-4. I just prefer it over there. It's all the same. And so then we're going to have a mystery particle. So we have 1, 2, 2 that's satisfied. So we're going to add 0. And then 1, 2, 3, 4, 5, 4, we have 1. And we have 0 protons, but all the neutrons plus protons added together is 1. That's just going to give us 1 neutron. And then I'm going to put a little gamma here just for energy. And that's just going to be an assumption, not needed. Just makes me feel good. So now, complete what is the name of the new particle released? So this is a neutron. This is an alpha particle. And then there's probably electrons, which I left off. Determine the mass defect of a single reaction, given the following information. All right, and then they give us the mass of all these atoms in atomic mass units. And so the idea here is the mass of an atom is not equal to the sum of all its component parts. Therefore, there's going to be what's called they say mass defect? Mass defect. That mass defect is going to be the energy released. So if we look at this as 2, 1 hydrogen plus 3, 1 hydrogen goes to 4, 2 helium plus 1, 0 neutron, we can add up these masses here. So this one is going to be 4.0026. This is going to be 1.087. And when we add those together, we get 5.0113. And then when we add these together, we get 5.030149. And sig figs, these are kind of challenging because usually what I do is I just take as many digits as I have available. It's the sort of thing where since you're taking a difference of 2 numbers that are very close together, you usually get a pretty small number. So for this, we're going to find the mass defect is equal to 0.018849. And this is atomic mass units. So here, we can now determine the mass defect. Bam, right there. Got it. Excellent. Determine the energy in joules released during a single fusion reaction. All right, so what we're going to do is we're going to convert this over to energy. And they asked us to do it in joules. So we're going to say that energy equals mc squared. Our mass is going to be 0.018849 atomic mass units. And we want to convert this over to joules. So we'll do Wolfram alpha. Let's look at AMU to kilograms. And 1 AMU is 1.66 times 10 to the negative 27th kilograms. So it's going to be 1.66 times 10 to the negative 27th kilograms, very small, per AMU. And that gives us...
That's just the mass of the proton.
So Terrence, can you say why he needs to convert to kilograms?
I guess he doesn't, but he's just trying to find the... he's just trying to use it in SI units right now.
Oh, okay, I got you.
Atomic mass units. Or this gives us mass. And then I'm just going to use 3 times 10 to the 8th for the speed of light. That's going to be in meters per second. That's going to be quantity squared. So going back to Wolfram, we will do 0.018849 times 1.66 times 10 to the negative 27th times 3, I'll do quantity, 3 times 10 to the 8th quantity squared. And I get a small number. Yes, seems reasonable because it's just one fusion. 2 lonely atoms come together and fusion. Not a lot of energy. Especially in terms of, well, it's a lot of energy.
So we get some.
Relatively.
So this was just a demonstration for you guys, especially for the layman who kind of want to see some real physics behind what actually you can do to calculate some basic quantities for fusion. And you get to use, of course, the nice little Einstein equals MC squared equation. And he just basically shows you that the binding energy gave him some order of 10 to the minus 12 joules answer. So then you can scale it up and you can actually get the numbers for how many of those reactions you'll need to, let's say, achieve enough energy for one household. And then even scale it up. I think further on he goes to show how much you need to power some nation or something. And those are on the order of gigajoules for how much people consume per year. And then it's on the order of like 10 to the 20th joules when you're trying to power some kind of nation. And I think I did the calculation as well for the United States, and it was like we needed some like 10 to the 19th joules or something I calculated for 300 million people if they all consumed, I think, 39 gigajoules of energy. So those are just a little bit of ideas of how much energy you need for this kind of stuff.
Yeah. So why? So what is the byproduct again?
So the product that you release with 2 deuterium atoms, so it's as you would probably think, it's a helium-4 atom, but then of course a helium-4 is just composed of two protons and 2 neutrons. So then there's an extra, I think, neutron that comes out of that. Because I guess it's a deuterium and a tritium is what they did. So you get an extra neutron, and then you also get a gamma, which is a photon. And that gamma, the photon, was basically what the mass defect answer was that he calculated. That's where the binding energy would be stored. I think, yeah. Because that's just the energy that's released, the extra heat energy that's released.
Yeah.
And that's actually what you would use to actually
heat up the water.
Yeah, to do the work. Yeah, to heat up the water. So like we mentioned in other videos, these fusion reactors are just glorified steam engines. Like all these high level things is basically at the end of the day just turn into a steam engine. So all you're doing with the fusion reaction is just getting this crazy yield of energy to turn it into heat, to heat up water, to turn it to steam, which powers some turbine. And that's it. But the beauty of the fusion reaction is you're supposed to get, hopefully, more energy than you output, or at least break even. With all of our other energy sources nowadays, like fission or whatever, the nuclear reactors that exist today, everything yields less energy than it takes in.
Than input, yeah.
Yeah, and you might think, like, why the hell is that useful? Well, it's just for the fact that you can actually do what you want with that energy, right? So you can take it from the sun, and then that energy from the sun, you'll be able to convert that into something else and use it whenever you want. So it's just the ability to be able to use it and manipulate it whenever you would like.
And so the byproduct again, you said it was helium-4?
Yeah, it was helium-4. That's what we want, and then also the neutron and then the gamma.
Because the thing is, like, I'm trying to think, like, we have a helium shortage, right?
Right, yeah.
Yeah,
So that would probably be beneficial to produce more helium as well. Right. I don't know if it'd be in enough numbers, but I maybe enough. If you're producing, 10 to the 20th atoms of helium, or I don't know if that's actually right. I'm sorry. I'm thinking of the joule calculation. I don't know how many atoms are produced, but however many number of
I think the helium
reactions.
that's useful for us is helium-3.
Okay. Yeah.
Yeah. So maybe we would have to break it down further or something.
Yeah. So if you could somehow convert that, maybe it'd be useful.
Yeah.
But yeah, we actually need helium for a lot of experiments. Is what Juan's trying to get at. He's trying to think of some business ventures.
Business ideas. Hey, maybe we can turn this profit around if you're a business guy.
Right. But with fusion, I mean, there's going to be so many of your problems that would be solved that it wouldn't probably even matter, because just the amount of energy that anybody can use would just be absurd.
So what's the hard part? So now that we know this, it's like, okay,
Right.
It's possible. What's the problem?
So the hard part is actually to getting that sustainable reaction. So with fusion reactors currently that exist today, like we have the Stellarator Wendelstein X that just got proved to be efficient. There's many other fusion type reactors, all of them experimental pretty much. they just don't last long enough. Like they can produce a reaction maybe on the orders of seconds or minutes, but there's all kinds of issues with plasma confinement. Let's say if you're a tokamak type fusion reactor, there's a plasma soup basically that's confined with magnetic fields.
So now we're talking about plasmas?
Yeah.
What the hell?
Okay, so plasma is just basically like if you imagine a proton or a hydrogen atom, right? A hydrogen is composed of an electron and a proton. Just strip all the components away from each other, and now it's plasma. So a hydrogen atom that strips away the electron and the proton, and you make it just,
It's just a soup.
Soup. Now it's just a soup of particles. So that's a plasma. And that plasma is what they use in tokamak reactors to actually get them highly energetic enough to be able to combine with each other to create that fusion reaction. And yeah, you get problems with turbulence. You get problems with that plasma quenching, and you also get problems with generating enough magnetic field, for instance, which the Wendelstein X is one of these reactors that actually tries to solve that problem. And this is just some extra details, but that's basically the problems with fusion right now. It's like,
Well, because I'm actually curious, because the plasma quenching thing is like, I'm imagining that. Okay, so the plasma is the current. Sorry, I'm getting ahead of myself. Protons and electrons, right? Kind
Yeah.
of flowing. Ideally,
Yeah.
it's a free flow.
yeah,
And then, as some of you may or may not know, when how would you say, when positive or negative ions are flowing, you're going to create a magnetic field, right?
sure.
Yeah.
Yeah.
And so
I didn't even think of that. And so you're saying that that's why you're getting those.
Because quenching, what happens in traditional magnets is quenching is whenever the magnet, usually it's supercooled, but the current that's flowing through a superconducting magnet or something, it overheats.
Yeah.
And it boils
Right.
off a lot of the helium, and then boom, you
Exactly.
quench the magnet.
Exactly.
I imagine this was happening here.
So I'm not sure exactly. I didn't look into that deep, but the plasma quench term, I believe, actually just I think it references the boiling off of the neutrons in that system, and I think it happens just from. Maybe it is related to what you're saying. I didn't even think about that.
I'm just trying to think through this. I don't know, but
Yeah, I think that's really interesting. Ideas you had there, and maybe actually even there's some issues with turbulence and whatnot because of those magnetic fields that you were talking about that were generated from the moving charge of the plasma. This is kind of deeper though for me, so I can't really answer these questions. But those are all really good observations, and maybe somebody who has some insight into fusion processes would say, but I don't know actually.
Let's bring it. If you're a plasma physicist, come on the show.
Yeah.
We'll have a million questions.
But of course, this stuff is related to magnetohydrodynamics, so you already know it's going to be hell, right?
Yeah,
Any
that's
kind of fluid type systems are already just chaotic and just a mess. So
that's a very active topic of research. If you guys don't know, magnetohydrodynamics is basically plasma flow, essentially.
And anytime you see fluids in physics, kiss your ass goodbye, because it's always
chaotic.
It's always this hard shit to deal with.
Yeah, it's a stochastic system, and actually slightly related. Go ahead and look at the last Nobel Prize that this guy.
True. Episode 136.
136, yes. Episode 136, the Nobel Prize was given to, in 2021, was given to...
Giorgio Parisi. Who invented that replica symmetry breaking. But let's not get too off the beaten trail.
But anyway, maybe this, speculating here.
Yeah.
Maybe there might be feedback between the two.
Huh?
Maybe his work could also help some of the fluid dynamics stuff.
I made a Twitter post saying, why didn't Salvatore Pais get the Nobel Prize when he invented nuclear fusion, room temperature superconducting, and
seriously,
and gravitational waves?
Seriously,
you would think somebody like that would get at least a little recognition.
The emoji. What is that emoji that has this?
The skeptical smiley emoji.
Yeah. Question. Curious.
But now we're gonna stop.
We'll stop.
Unbiased.
Yeah, we're unbiased.
Anyway,
we're like Fox News. We report, you decide.
A great comparison.
Anyway, I'm kidding.
Yeah.
But yeah. So okay. So that's the hard part.
Yeah.
But, so where does Pais come in? Like how does he play into all this?
So Pais basically circumnavigates all of modern fusion research.
Conveniently.
Well, he doesn't circumnavigate it, but he seems like he jumps ahead by many decades.
You activated my trap code.
Right. Because he basically skips all the way to a plasma compression fusion device, which is a compact fusion device, which is interesting because basically one of the biggest modern iterations of fusion that's going to have the most promise, I guess, besides the Wendelstein X, which is a more mysterious one, is the ITER project, which is ITER, which is our basic, it's like a 35 nation giant 25 billion project, 25 to 80 billion dollar project, tokamak type fusion reactor, and that's the modern frontier of fusion research right now. So it's thousands of people, all in collaboration, again, from 35 different countries, billions of dollars of research, giant fusion reactor. I mean, it's several stories tall, and Pais somehow navigates through all of this and jumps right to a compact fusion reactor, that could fit into a vehicle, or of some type. So needless to say, we're a little skeptical.
Curious.
But, let's go ahead. I mean, I guess this is the opportunity to jump into the patent or into the research. So basically, if you know Salvatore Pais, he did a bunch of patents, but he actually wrote an IEEE paper on this fusion device.
Yeah, it's called it's the IEEE Transactions on Plasma Science. And
the paper title is the Plasma Compression Fusion Device Enabling Nuclear Fusion in Ignition. So it's got a lot of exposition, introduction and whatnot, but I wanted to kind of jump straight to the part 2 section.
Well, as in any good research paper, you go straight to the conclusion.
Right.
So I'm gonna read like the last couple sentences here. The plasma compression fusion device concept can produce power in the gigawatt to terawatt range and higher, with input power in the kilowatt to megawatt range, and can possibly lead to ignition, meaning he says self-sustained plasma burn.
Mm-hmm. Which is the hard part of plasma fusion research.
Like Terrence was saying, yeah. So several important practical engineering and operational issues with operating a device such as he calls it the PCFD, the plasma compression fusion device, are discussed.
All right.
So which part do we go to? Let's see.
Yeah, Juan. So jump down to that part 2, enablement of concept, right there. So it's about a page and a half. I figured we could step through each of the paragraphs and just read them real slowly, and I can kind of expound upon what's actually going on and try to build this mental image.
Yeah, so he's saying in figure 1, the preferred embodiment of this original concept, the PCFD, uses a hollow cross duct configuration of circular cross-section, which the concentrated magnetic energy flux from 2 pairs of opposing curved-headed, counter-spinning conical structures whose outer surfaces are electrically charged, compress a gaseous mixture of fusion fueled into plasma, heated to extreme temperatures and pressures.
Yeah, read it slow. So
by the way, and I'm doing that. I'm reading it that way because the man did not pause one. He did not create.
Right. This is not unheard of in physics. Sometimes wordy talking about shit actually doesn't really help that much.
Yeah, so
it's better to just see an image. So I figured maybe I can describe it better.
No, trust me, I literally have this problem. Okay, you're gonna see this differentiation because for me, I like writing the facts. I don't do a lot of this kind of stuff. I try to make it as succinct as possible.
Right.
But some writers, But anyway, in this figure, what he's really showing is, and if you're a visual podcast viewer, you're gonna have a nice little picture, but for the audio listeners, what you're seeing in better words than his, I think, imagine like a cross, and in that cross you have the center. You have a fusion plasma core that's encased in a vacuum chamber, essentially.
So that cross is the vacuum chamber, like if you imagine a hollowed out cross.
Yeah, and so and then there's in all the 4 crosses are basically deuterium gas injectors.
Well, you can say they're these metallic, like if you imagine like electromagnets, they have like these, they're like electromagnets, but they have these cone heads, these conical heads on them. And I guess that's because of the magnetic field shape. I'm not entirely sure, but I would assume it's because he's trying to get some kind of particular magnetic field shape. And these conical structures are actually inside of this cross, this metallic cross, and basically they rotate. So they're rotating conical structures that basically generate magnetic fields, and they also inject the deuterium into the chamber there,
yeah.
and then they all get sent to the center to make this kind of compressed plasma ball, essentially. And the conical structures rotate. He calls them counter-rotating. I didn't really see how they were counter-rotating from the image, because they both looked like they were rotating in the same direction from his drawing.
Yeah.
But needless to say, he calls them counter-rotating conical structures, and I assume that's to alleviate some kind of turbulence from the plasma that's or from the deuterium that's injected into that core there. Anyway, continuing on.
Yeah, yeah. And so he says the PCFD uses controlled motion of electrically charged matter through accelerated vibration or accelerated spin subjected to smooth yet rapid acceleration, deceleration, acceleration transients. So yeah, so to generate extremely high energy, high intensity electromagnetic fields, which not only confine the plasma but also greatly compress it.
Yes, so he's saying that these EM fields generated by these conical electromagnet type things are compressing the magnet as well as keeping it confined, or compressing the plasma as well as keeping it confined.
So this allows it to produce a high power density plasma burn, leading to ignition or self-sustained.
Right. Ignition is that key word there of the sustained reaction of plasma, basically. So he's claiming that it's a sustained reaction.
Yeah, I'm going to try to break that down because he says. So it sounds to me like he's saying that it's a controlled motion of electrically charged matter through accelerated vibration. So he's like rotating this. I'm not sure.
Yeah, it's a little bit strange. The vibration part also comes in with the actual cross. So the cross is like some cavity, and this is where he invokes one of his other experiments. The piezoelectric room temperature superconductor is the material that makes up the inner cross section, and I think he also uses that for containment as well. I think specifically for the neutron containment, because with fusion reactions, remember from that video we saw, they release a neutron, right? And I think that's actually responsible for heating. That's actually the main component responsible for heating that, for heating the reaction, for making it so that you can transfer that energy out. And he uses that vibrating chamber, I guess, to contain those neutrons. This is a guess.
Yeah, but anyway, let's keep going here. He says the generated high-intensity electromagnetic radiation heats the plasma, and the produced magnetic fields confine it between the counterspinning conical structures he calls them dynamic fusers.
Yeah, so we can actually go or talk about fusers a little bit. So fusers are interesting because they're like they're a particular kind of way to generate fusion. I actually have a Wikipedia article if you want to look at it too, one of what fusers are. I got an image. So a fuser, basically, I got a simplified image here of a fuser. So basically, if you imagine two rings, this is the general principle behind fusers. So in section 1, actually, you can even read it here.
Yeah, it says the fuser, and there's a picture here. It's a circle.
Yeah. Well, two circles. There's a blue circle and a red circle.
Oh, yes, thank you. Yeah. So, and then there's lines going into the blue circle, the smaller blue circle inside of the bigger red circle.
And those are basically the vector field, the electric field.
Gotcha. Yeah, so it says the fuser contains two concentric wire cages. The cathode is inside the anode. So the cathode is the
negative.
Yeah, the blue one.
ring. Right.
And then the anode is the red one, which is on the outside.
Right, which is the positively charged ring.
Yeah, so the positive ions are attracted to the inner cathode and they fall down the voltage drop.
Mm-hmm.
Now, the electric field does work on the ions, heating them to fusion conditions.
Mm-hmm.
And then the ions miss the inner cage and then they
Which
collide.
is the blue ring.
Yeah, so they collide in the center and then they may fuse.
Right. So this is basically what I think Pice is trying to do, in more words or less. So he's using these conical structures to basically boil off these deuterium ions, essentially, and then accelerate them into the center to where they're going to have these collisions, just like a fuser would do, in some sense. But then I guess he's got it a little bit different because he's also got a plasma in the center. But I guess that plasma also happens in the fuser. I'm just not exactly sure on a fuser. But yeah, he's kind of got like a fuser type device here in some sense.
Yeah, so he says it's important that the cross-duct inner surface surrounding the plasma core region is electrically charged and vibrated to prevent the plasma from impacting the walls and initiating a plasma quench. So basically, the plasma quenching would mean that the state that gives you the plasma is nullified. It disappears, right?
I guess.
With the quench the plasma, you don't have the plasma anymore.
Yeah, I think so. And then that makes it so that your ignition fails or something.
Yeah. So vibration can be achieved by passing an electrical current through piezoelectric films, such as lead zirconate titanate (PZT),
This is him referencing his other patents.
embedded in the PCFD duct inner wall. So the PCFD device is housed in a Faraday cage for reasons of personal safety. By the way, a lot of grammatical errors, I will say.
Yeah, personnel safety.
Personnel safety and also embedded.
Oh yeah, yeah.
Anyway.
But I mean, look at any foreign. Well, not to be insensitive, but look at any foreign physicists' research papers, and they're wrought with grammatical errors.
You know, that's not I'm being a little highfalutin.
Yeah, yeah.
So
This is not unusual for physicists. They can't
No,
spell
it's
for
not.
shit.
It's fine. They're not English. They didn't go into English. It's
Yeah.
fine. A 10 to 15 centimeter thick boron carbide or tungsten alloy shielding, which acts as the Faraday cage, can also incorporate the cooling channels for the thermal conversion cycle, as well as provide the needed structural support and integrity to withstand the fusion-induced neutron bombardment.
Whatever.
Yeah, so plasma instabilities would be minimized and possibly suppressed by the shearing flows generated by the counterspinning dynamic fusers.
So this is kind of important because this is telling you why those fusers
Yeah.
or those those conical electromagnets are spinning. So he's claiming that basically you're getting rid of those shearing flows, which is one of those turbulence issues that you see with fusion reactors. So he's saying that simple rotation motion is getting rid of the turbulence.
Stabilize the plasma, I guess.
Right, and something that simple to me would seem like really I don't think so, because people probably would have tried that already. But what I'm thinking is maybe that his EM fields are so high intensity that basically the turbulence is almost minimized, because really the biggest part of containment are those high intensity electromagnetic fields.
Yeah.
So you can get around the issues of turbulence because he has this fuser type reactor, I guess, and it's not as relevant in this system, especially when you have such high intensity EM fields.
Yeah, he says the flow shearing would tear apart the vortical eddies responsible for the onset of turbulence within the plasma, which is regarded as the main source of plasma instabilities in fusion reactions, and he cites like 3 papers.
Yep.
Now, eddies, so for people that don't know.
Yeah. Oh, those are just currents that get generated so eddy currents, I don't know if it's really that relevant here, but
Just to kind of get a mental
it's
picture.
like
It's
like
electro-
vortical currents. They're usually something you don't want in a system, right? They're usually unwanted in a system, but they're like vortical currents, which you can see them in all kinds of systems. Like a lot of times in condensed matter, you'll see them in superconductors.
Yeah.
They'll have like extraneous eddy currents.
Yeah,
And-
they flow. Essentially, they flow in closed loops within conductors in planes perpendicular to the magnetic field. So
Right.
there's a good picture here that we'll throw up for the listeners. But
for the visual people.
For the visual, the
the
listeners.
YouTubers.
The listeners, I'm sorry to say, but I can't really describe this. What I'm seeing.
Yeah, just know that there's these
it's like
vertical currents.
I guess it's like the whirlpool, like a water analogy is like they're like whirlpools
Sure. Okay. Whirlpools of current.
of current. Yeah.
Yeah. Anyway.
So yeah, Figure 2, he says, shows an even more compact version of the concept, which uses vibration and in a linear duct configuration, featuring 2 counter-spinning dynamic fusers only, and would be best suited for fusion power generation on aircraft or main battle tanks.
Right. So he's claiming that basically this.
You only really
fusion-
need 2, is what he's trying to say.
Right. Like he's simplified versions of this. I mean, they look really simple, but
Then why would you even need 4?
well, I guess
Do you know what I mean?
maybe it's more stable, the 4, or more powerful.
We'll see. I don't know. For both configurations, the fusion power output is extracted through conformal heat exchangers, which are flush with the PCFD outer walls and carry the neutron-produced heat to a thermoelectric generator through a cooling fluid such as water or some other kind
So
of
I think this is
frozen
just
water.
describing like how it's going to actually power the systems. Like we said,
Right.
it's heating something up and then turning it into steam from water.
The fusion fuel, preferably deuterium gas, is introduced into the plasma core through the counterspinning conical structures, namely injected through orifices in the dynamic fuser heads. Deuterium, or heavy hydrogen, can be abundantly extracted from seawater, hence the virtually limitless fuel source, which makes this extremely beneficial.
Right. So he chose a deuterium reaction because of its just the abundance of deuterium. The lowest energy fusion reaction is deuterium tritium, but then the next
Yeah.
form would be deuterium.
This one?
The PCFD.
Yeah, the PCFD will use deuterium 2H gas as a fusion fuel of choice, yielding reactions, and then he has
They both yield some helium-3 reactions, one with a neutron or one with a proton. Basically, you want the one with the neutron.
So it's feasible to use both direct electrical and indirect thermal energy conversion using deuterium gas, which is highly desirable. As shown in Figure 3, the dynamic fusers can be assemblies of electrical grids and toroidal magnetic coils arranged within a conical structure whose outer surface is electrically charged. The electrical grids are used to ionize the deuterium gas and are kept at different oppositely charged voltages so as to electrostatically accelerate either electrons or ions into the fusion plasma core depending on the desired physical effect in a manner similar to ion thrusters.
Oh, the ion thruster makes a scene. But yeah, I guess that one's just saying like the deuterium comes out neutral, but then you can just ionize the deuterium atoms, which is just strip off an electron and then accelerate it into those fusers, and then those fusers will actually expel the deuterium towards that center region and confining it and then making the plasma.
So the dynamic fusers can act as particle accelerators for electrons that are closely bound to the magnetic field lines of the inner toroidal coil, as well as to the magnetic field lines of the conical structure once they exit the dynamical fuser. These electrons are electrostatically accelerated through a set of 2 grids exhibiting a potential difference into the plasma core, forming a deep, high-energy, negative potential well. The potential well greatly accelerates the positively charged ions towards it, and the ions keep recirculating around the wall, and that way they undergo fusion. So kind of like what you were saying about the fusers.
Yeah.
Yeah. So he's
just kind of
describing it there.
describing more detail the fusers themselves and how they actually accelerate the deuterium atoms into the center.
So he says a high temperature, high pressure plasma core results from the impingement of gas dynamic vortical plumes, which exhibit high viscous heating, as well as the intense collisions of electrons and positively charged ions which make up these plumes. To heat the plasma at the extreme temperatures that fusion requires, the electrically charged dynamic fusers generate high electromagnetic radiation by virtue of the accelerating spin. God.
Yeah, I didn't really understand that part.
To heat the plasma at extreme temperatures, that fusion requires the electrically charged dynamic fusers generate high electromagnetic radiation by virtue of the accelerating spin.
Let's skip.
Yeah, I mean, he just kind of talks about the details a little bit more.
Yep.
Um,
He says dynamic fuser is mounted on a hollow shaft deuterium gas conduit, which is coupled to a variable power DC induction motor and can be accelerated, decelerated, accelerated, and spin through a digital controller. The PCFD must be a vacuum pump for fusion power to be effectively produced. So it just needs to be under a vacuum, which is expected. I mean, all fusion systems need to be under vacuum, so it's not unusual.
so you don't you don't ionize the air,
And I mean, yeah, you have a bunch of extraneous shit in air, so you need to have
nitrogen
enough.
and oxygen and shit.
Yeah, so it's like that's an obvious thing, but just for completion's sake, that's pretty much all I wanted to read on that section. And I guess the final part I wanted to read was just he has a section on the potential problems with the PCFD.
Yeah, he calls
Four.
it possible operational issues.
Yeah, so you can
The
read
design.
a few of those paragraphs.
He says there are several important practical engineering and operating issues with operating a device such as the PCFD. First, the deuterium-tritium triple product given in the equation he says here will be much higher by at least 2 orders of magnitude for the deuterium-deuterium reaction envisioned in the PCFD fusion reaction. This is due to the fact that the plasma physics presented herein is oversimplistic, with little, if any, consideration to plasma transport or instabilities which degrade the achievable triple product. Further theoretical research would have to be performed to give consideration to the impact of the extremely high neutron flux anticipated in the DD reaction, even though this will peak at lower energy than for deuterium-tritium. And even proton-boron fusion is not without neutron issues due to the byproducts and the boron isotope production, I guess.
So I don't really know what he's saying there, but I'm just getting that the tritium reaction can produce more. That was already a given because the tritium reaction is the lowest energy configuration, so that's not really saying that much to me.
So for the DD, the deuterium-deuterium reaction, which is the reaction of choice for our present concept, the triple product, and he gives some equations here. What is
Yeah, that's an important equation for gauging the effectiveness of fusion reactions. I think it's called Lawson's or equation or something, or it's a commonly used thing, the triple product, to see how well the reaction will yield. I actually have a chart on that I put for Wikipedia just to show you.
Yeah.
And it was I think it was Wikipedia chart. Yeah. Lawson's criteria, I believe, is what it's called, and this is just a chart of some of the
Reactors? Or what is
the
this?
reactors and their Lawson criteria mapped on the triple product diagram.
Yeah. So they have the chart's actually really nice. If you folks, for the listeners, it's got a time on an axis, and you can see that we've actually gotten better triple products. And by triple products, what fusion triple products? What do you mean?
Well, you saw that equation there. It had 3 variables. It was like NT and T sub or tau sub E or something. So it's the product of those 3 variables. So the higher that product, the better the fusion reaction is.
Yeah, so you can see it jump from orders of magnitude. Early on in the 70s, 60s even, you had 0.01 of this triple product in the units that is given or whatever, but by the time we hit the 90s, we jumped like 3 orders of magnitude.
Right.
Like, it's insane. 4 even.
Right.
Yeah, it's crazy.
So it is getting better for sure.
Yeah.
Yeah.
But what else? How do we go back to this? So then he says because the temperatures. Oh, sorry. Let me go back to what he said. So he says which is the reaction. The DD reaction is a choice for the concept that he's presenting, and he gives the number of the triple product here because the temperatures required for fusion in the DD reaction are far higher than those required for fusion in the deuterium-tritium DT reaction. And he says, as far as the plasma instabilities, magnetohydrodynamic, interchange, kink, or whatever, within the PCFD device are concerned, it is possible that such instabilities would be minimized and possibly suppressed by the shearing flows generated by the counterspinning dynamic fuser. So I guess that's kind of what he's betting on. He's betting that the dynamic fusers rotating would stabilize the plasma
Right.
from shearing forces.
Right.
From the
I don't really see how that's possible since it seems like the turbulence and shear forces and all that is such a hard problem in fusion. I feel real skeptical of that. Like the Wendelstein X is an example of a stellarator type fusion reactor where they have this crazy looking configuration for the magnetic fields just because of that weird, just trying to keep the plasma confined with these magnetic fields. It just seems too simple to just have a rotating conical head. It seems like somebody would have thought of that. But I don't know. I'm not a fusion guy. I don't know nuclear physics really that much. But it just seems, I'm skeptical of that claim.
I mean, I'm skeptical because it seems to me like, how would you have a vacuum and have something mechanical spinning? How do you even seal that?
Oh, that's interesting.
Do you know what I'm saying? Like the mechanical
Right.
limitations.
I didn't even think of that.
The mechanical limitations are like, I mean, well,
Maybe,
actually,
yeah,
I'm
go ahead.
thinking, so like, okay, so one way he could do it is he literally just has like a cross, whatever the design that he has, but they're just tubes.
Yeah.
But the thing is, these mechanical things or whatever, the deuterium injectors would actually have to be mechanically separated from the
Spinning conical heads.
yeah. So
Okay, well, he doesn't have that in his image. He
doesn't.
actually has them as one solid piece. I didn't even think of that. That's a good point, Juan. It's kind of hard to achieve a vacuum when you have like moving parts inside the vacuum, right?
Yeah.
Yeah, I don't know about that.
So I don't know. Maybe
It's an
that's,
interesting detail.
maybe that's kind of what's stalling because I can't imagine.
But we can even, I wasn't even thinking along the experimental lines. I was just trying to even humor him with the theoretical concept.
The theoretical stuff. I mean, it's a little bit beyond me, but
Yeah.
I'm thinking of the mechanical limitations, like you're saying. Like, if somebody had thought of this, I imagine experimentalists have because this is kind of
Yeah.
their forte.
I mean, people have been trying to come up with all kinds of clever stuff for
Yeah.
fusion. And I mean, we've been working on this problem for what, like 100 years now?
70s? No,
Yeah.
well, this says the 70s, but
Okay, 70s, that's still what? That's
50 years.
50 years.
Yeah.
So,
And the Russians, who knows when they were working on it?
right.
They're probably working on it in the 1800s. man.
Right.
I don't even know what,
you know, they always
You
have
literally- no, yeah. My joke is that if you look up any paper, the Russians probably did it first.
Right.
Like, you're like, oh yeah, the Soviet nation did that. So, crazy.
Yeah, go ahead.
But anyway, he says the induced flow shearing would tear apart the vortical eddies responsible for the onset of turbulence within the plasma, which is regarded as the main source. What the fuck? I thought we read this already.
Yeah,
He just reiterated it.
Okay.
Wow.
It's that important, I guess.
So we're jumping ahead here.
Yeah.
He says another possible issue with the PCFD is extremely high magnetic fields anticipated in operating it.
Yeah, so this was interesting to me because this is where he cites himself with 5 and 6.
Even though high intensity electromagnetic fields have shown to be theoretically feasible,
With his papers, 5 and 6.
experimental verification is necessary for proof of concept.
So that was an interesting one. That was probably the one that jumped out to me the most. Let's talk about that for a second. So he talks about these high intensity EM fields, but they're based on these concepts that haven't even been done yet. So he's referencing his papers on an inertial mass reduction device, as well as the, I think it was the, what's 5 and 6? Hold on.
Yeah, let's see. 5 and 6, yeah, both PAIs. The 5 is the high frequency gravitational waves induced propulsion.
Yep.
And 6 is a hybrid craft using an inertial mass modification device.
Yeah, so he references these high fields, but these are based on devices that don't even exist yet. Or at least we don't know if they exist. Maybe they do. Maybe the Navy's hiding them. But it's just interesting because he references his own paper on that. And it's kind of, I think his device is reliant on those things working.
Yeah, because he says here that, he says that, whatchamacallit? I'm not sure because he says the issue that them creating high magnetic fields in operating, like he basically is admitting that you need really high fields to stabilize this.
Yeah.
And to produce the high fields,
You
can
need
look
his
at my
magic device.
you can look at my stuff.
So, yeah.
I mean, the orders of magnitude I think he gives in the paper, right? He says
for the EM
Oh
fields?
no, he doesn't.
No, he doesn't. I don't think. I think he just uses the reference and doesn't mention them here.
Yeah, because that would be nice to know. I mean, what kind of or what order? Like the highest magnetic fields I think we can produce right now are like and that's pulse field are like
Yeah.
100 something Tesla,
Yeah.
and that's like
And
for
pulse
short
field means a
duration.
short duration, right?
Yeah.
I think the highest EM fields we can do for static are probably like 45 Tesla or something around there.
Yeah, I think maybe like 70,
No, I don't ever even seen
60.
that. No way.
Nah, I'm tripping.
Yeah, I think 45 is the highest I've seen.
I think there was a new one that got announced. In
Really?
Japan. I think Japan
Yeah,
has
that's
a high magnetic
45.
field lab.
That's 45, I believe.
Maybe so.
Yeah.
Yeah, because I know a new one just got put out, but it's a
Or maybe
super-
you're right. I'm not sure. I'm
superconducting.
thinking of actually the Max Planck Institute as one.
Yeah, because there's different types of fields. But anyway, and these are huge facilities
Yeah.
to house these magnetic fields,
Yeah,
by the way. We're
yeah.
talking about
Giant magnets too.
giant magnets housed in like huge cryostats.
Right. But Pice has invented his high EM generating device,
Yeah.
which I think is what he's getting at, is why he can make it compact. So his device that we don't know about is being referenced here. So he's building up devices on devices here. So it's linked with a lot of devices that you have to accept in order to accept this device.
He says, if indeed the controlled motion of electrically charged matter from solid to plasma under accelerated spin and subjected to rapid acceleration can produce the theoretically anticipated high energy fields necessary for optimal PCFD operation, then another major problem can arise, namely the possible structural failure of the device due to the strength of the material limits imposed by the generated B fields. I wish he would give the fields needed, but this is maybe a theoretical calculation that he can't.
He could have calculated it.
Because I don't know.
I
Because
presume.
maybe so, but I mean, if he's an engineer, I imagine he's like, "Hey, who wants to
To do the theory here.
But then the thing is, you'd have to give working numbers, right?
Yeah.
What we're talking about the plasma core.
Yeah.
You can make some assumptions, like how big is the plasma core,
Right. Right.
how many deuterium atoms, and like what's the minimum? Because maybe you can scale it, right?
Yeah, yeah.
You start
Well,
with-
here's the thing: the Fuser device I know can be built in like your own house.
Mm-hmm.
So there's a YouTube video of a guy who's built his own Fusion Fuser device.
Mm-hmm.
I think there was even like a 14-year-old kid or something who built his own Fuser device or something like that.
14-year-old Michio Kaku.
Right, pretty much.
Mm-hmm.
So I mean, the Fuser devices can be done with relatively, normal-ish gear. I mean, you'll need some like vacuum pumps and whatnot, diffusion pumps, which is expensive, but you can build them. You can build them in your house.
Yeah.
But the fact that nobody's thought about this compact fusion device with this particular configuration, I'm assuming
'cause it
Pice stands out because of its high EM fields. Because
it rests on the fact that you need high magnetic fields.
right,
to stabilize.
right. And I'm not a nuclear physicist, so I don't know this for sure, but just like his geometries don't seem to stand out in any particular way. Like if you look at the Wendelstein X Stellarator, that's a crazy geometric configuration that they need to contain these fields. So obviously, I don't think it should be the geometry. So then the only other thing there's really only two components: it's the magnetic fields and then the geometry. And I think his claim to achieve this kind of fusion device is the EM fields.
Gotcha. Yeah, he says here the ability of the PCFD device to produce extremely high magnetic fields can shape the plasma core in a configuration conductive to a high possibility of self-sustained plasma fusion. And then I'm gonna skip ahead, but essentially what he's saying that he says that because it's going to generate these really high fields that haven't really been tested structurally. And he says the generation
They've been not. If we remember the last time when he was talking about the fields he can generate, I'm assuming it's the same fields. They are on the order of magnetars, right?
Well, he's saying here the generation of very high B fields in order of 1,000 Tesla.
Yeah, that's like magnetar level. These are like celestial objects, that are like giant objects in the universe that we've not seen and that we see on like very far away from the Earth.
Yeah, he says in this case this charged matter is a plasma, it can be readily observed that the V squared term is directly proportional to the plasma oscillation frequency and directly proportional to the plasma okay, whatever. So
Yeah.
he says the plasma B fields can be obtained by increasing both the angular frequency of the vibration of the dynamic fusers and the plasma density. The only limiting factor in the case of the PCFD design is the structural integrity of the fusion device.
Mm-hmm.
That the B fields exceed 1,000 Tesla.
Right. So basically, he's just saying that he's not even claiming that he can't do his B fields. He's saying that he can do these B fields, but it's just as long as his device can take the infrastructure of the device can take those fields, which seems kind of the inverse to me. I'm like, I feel like don't worry so much about the device structure, Pice. Maybe worry about proving how you could get 1,000 Tesla
1,000
fields.
Tesla?
Yeah, that's just nuts. Like as we
That's
said,
so much.
45 Teslas, 100 Tesla in a pulse field is the biggest we've seen on so far in modern physics research at every other level besides the secretive Navy stuff, I guess you could say. Which typically, guys, I mean, I feel like usually the normal the physicists in research are going to be on the leading edge as opposed to Navy or government, but maybe not.
With fields that high, like would the blood in your body like be like pulled to one side and you'll be like,
Yeah, I wouldn't want to be in that field. You would be you'd have a bad day, I would imagine.
oh, you would probably have a stroke.
Yeah.
Like in that. Like I'm not even kidding. 1,000 Tesla.
Yeah, I wouldn't want to
insane.
try that.
I mean, like it. I mean, B fields precipitously fall. I mean, it falls like R squared, right?
Yeah.
So it's like
Juan's
but-
talking about the distance you stand away.
yeah,
It's proportional to the inverse square law.
yeah. But even then, 1,000 Tesla.
Yeah. I wouldn't want to mess with that.
Even with like I've been in the presence of high magnetic fields and it's like you see the lines like extend.
Right.
I'm like you have to be a football field away from.
Well, also remember, Pius said it's in a Faraday cage, so don't worry.
Oh, okay.
But no, I don't even think a Faraday cage is gonna help there.
That's insane.
But yeah, so this patent has made. I mean, this device is built on the thing here is this device is built on other technologies that don't exist that are already insane.
Mm-hmm.
So it's just like, yeah, his idea to me, the first things it makes me think of are like Star Trek technobabble.
Mm-hmm.
Like they sound legit because it's based on realish physics, but the crazy shit they just fill in with things that could potentially maybe exist. Like he's like, we don't have 1,000 Tesla fields, but let's just say we did. What could we make? That's what it kind of feels like. It's like a Star Trek-esque type paper. It seems like to me. I mean, what would you say, Juan? Just
I mean, just
your own conclusions here.
I mean, my conclusion is that he his proof of concept first needs to be sorted out before he even gets to this point.
Yeah.
Gets to even write this paper, to be honest,
Mm-hmm.
because I think you have to have. Look, I can pontificate all day. I would love to have his job if he can just write proof of concept stuff.
Right. Well, this research actually was unrelated to his Navy stuff, apparently.
Oh, was it? Okay.
Yeah, he said this is kind of his own.
Hmm.
It's of course he's using some of the same patents from his Navy work, but
Yeah.
he's saying that this was unrelated to the research, I guess, that he was funded for in the Navy.
Oh, interesting. But he's building up on it, so I don't
Yeah.
know. I mean, first you need to see if he can actually produce high magnetic fields using his little piezoelectric.
Well, not that one. It's something
it's not that
else.
one, it's
I think
something
it's one of the gravitational.
Oh,
I
it's
think
the inertial mass thing.
yeah, it's related to that one or something, or maybe the gravity one because I don't remember exactly.
I don't remember either, but
yeah,
but one of those, whatever he used to generate these
Yeah.
high electromagnetic fields, he needs to sort that out first because
Yeah.
then maybe we can talk about making plasma fusion reactors.
right. He's kind of putting the cart before the horse, right?
Yeah,
He's
yeah.
making all these huge claims with things that we don't really even know if they can exist or not.
Yeah. I mean the most famous one today is which one? I see you saw ITER or you had ITER.
Yeah, ITER is the most famous tokamak. Wendelstein X is a very promising, big leaguer these days. There's also a compact fusion device that Lockheed's doing with Skunk Works. So that was interesting to see.
is
But
interesting.
I think I think they're really in their infancy, and it's not even close to anything that Pice is making claims for. It's like a very, very heavily research-focused compact fusion device. And
Wow, Lockheed Martin,
Lockheed Martin.
turning They're really trying to help humanity out with fusion reactors or something else.
Oh, I see. Turning a new leaf, as opposed to blowing up people in Afghanistan.
Hey, Lockheed Martin, I'm on the market. I'm just saying. I'm not going to say anything bad, but if you're working on plasma fusion reactors to help humanity,
Right.
maybe I can forgive all your past transgressions. Your crimes against humanity. I'm kidding, but anyway. Yeah, what was your take from Pice?
I just think it's really bold claims, man. I'm inclined not to believe. I'll be honest. Of course, I like to always reserve full judgment until I know all the facts. So I mean, maybe Pice does have some kind of tech, but I mean, just knowing that the smartest guys and gals working on this problem aren't anywhere even close to what Pice is claiming. Like, his invention seems decades at least off, like 40, 50 years. And this is a generous number, I think. It could be, way more advanced even than that. Especially with making claims of generating 1,000 Tesla fields. I mean, this is just like, I don't even know a pathway to physics that really even explains that. So
Yeah.
I just don't see it as being realistic, honestly. And I mean, if you look at just reference the Uri Geller situation when we talked about with remote viewing and things. I mean, just because it's the Navy doesn't mean it's legit, guys. I mean, there are crazy guys that can do things in the Navy and it can be taken seriously because, I mean, they're military guys. They don't know that much. I mean, let's be
they're
honest.
engineer
They don't really
guys,
know
but
that stuff.
they might not know. What Terrence is trying to say is that they're engineers, so they might not know a lot of science.
Yeah, they can get had by physicists. They can get had. I mean, and also an interesting note was that they did dump $500,000 in this project with Pice at one point with the Pice effect, but I think they have since stopped funding research for it. So that tells you something as well, that they weren't able to produce any of the claims, I think,
Or
that were
reproduce.
reproduce any of the claims that were being made by Pice. So I'm leaning probably around a high 80% that Pice is bullshit, but I don't know for sure. So I'm
Hey,
going to reserve that 20% just in
Yeah,
case.
20% would be in case Pice decides to come on the show.
Mm.
This is an invitation, Pice. If you're watching this,
Right.
yeah, we might that 20%. Maybe you can be a little bit more convincing if you come on the show.
Right. We might hand you that 20%, Pice. Just saying. Come on the show.
But with that being said, any closing statements? Or is that pretty much it? Is that the bow on it?
I think that's the bow, man. Yeah.
I think I agree with you, man. It's he's got to put up or shut up.
Yeah.
The papers aren't convincing enough, and he's got to show something. He's got to go into Times Square.
Right.
Him
But I
just-
guess you could always make the claim that it's Navy and secretive, so he doesn't want you to know, right? Because this is
National-
leading tech stuff.
Yeah, national security.
Right, national security issues. So, I mean, you can always fall back on that, right? So, the Navy won't comment either, so
What are you gonna
more
do?
mystery, like all this UFO kind of stuff.
So if you're a UFO person watching this, the answer is no. You're not. Pice hasn't really made a fusion device. Right?
Well, we're going to be fair and just say
Okay.
we don't think so.
we don't think so.
Yeah.
Okay.
But
Fair enough.
maybe.
Maybe.
Can't rule it out just yet.
But with that being said, folks, make sure to like, comment, share, subscribe.
Indeed. Check out eigenbros.com, eigenbros on Instagram, eigenbros on Twitter, eigenbros2 on TikTok. And then patrons, thank you guys once again.
Seriously.
Guys, it really helps us when you help support this channel. Me and Juan are going to try to make this possible as long as we possibly can. So, if you want to donate, it won't be a wasted effort.
It will not.
We give you one audio podcast every week. And if you want to become a Patreon, patreon.com/eigenbros. And then we also get you access to the Discord. And
You can talk to us directly,
Yes.
ask advice, mostly what not to do,
right. Which is useful.
which is useful. We've been through it. But anyway, but yeah,
I think that's it.
that's it. All right.
All
Talk
right.
to you
Later, folks.
Bye-bye.